size. Like, is this okay? Maybe I'll try to look it up.
Yeah. Yeah. Okay. Hello, everyone, and welcome to the Bangalore Theory Seminar Series. This will be a two-part talk. Till 12:30, we'll have the first part, and then we'll have lunch, and then at 1 p.m. we'll start again for a 1 hour talk. Uh, so today we have with us Arpit Agarwal as a speaker. Arpit is a assistant prof at IIT Bombay. Before joining IIT Bombay, he did a postdoc at Fair Labs, which is a part of the Meta Group. And before that, he did a postdoc at Data Science Institute of Columbia University. He started off his PhD at IISc with Shivani Agarwal and then moved to UPenn along with Shivani. His research interests lie in area of ML and AI, specifically in the interaction of humans with ML and AI systems. Today, he'll be talking about semi-bandit learning for monotone stochastic optimization. Over to you, Arpit.
Thanks for the introduction. Very nice to have to be back. And I guess this is the first time I'm seeing this room. So pretty excited. Thanks everyone for showing up in the holiday season. Uh, I'm pretty unprepared for this this lecture, so don't ask any tough questions. Uh, but okay, so the plan is to talk about my recent research, which is on uh, offline to online conversions for stochastic optimization problems. So this I'll specifically be talking about a paper that appeared in Fox this year. But I thought I should give first a background on some of the relevant uh, some of the relevant literature. So in this lecture, I'll first talk about multi-arm bandits, which is sort of crucial to understanding the second part, which we'll talk about arm. Okay, so let's get started with multi-arm bandits. And I don't know how much, at what pace should I go through this, because maybe many of you are already aware of this. So please let me know if I'm going too slow, too fast. So, so this word multi-arm bandits is basically a very classical problem studied in many different areas. So the let's imagine a scenario that you are in a casino and you have $100 or 100 rupees, right? And there are some slot machines. You might have seen slot. You know what slot machine is, right? Like there is an arm handle, and you pull that arm, and you basically each machine charges $1, right, to pull, and you have $100, right? So, any thoughts how you should go about? Like you want to maximize your reward, and each machine has a distribution of rewards. Basically, let's call it Bernoulli distribution, and mean of machine I is mu1, and you have like let's say n machines. So, any thoughts on how you should go about pulling those arms and maximizing your reward?
The means are known.
Means unknown, then what should you do?
Highest mean.
You'll play the highest mean, maximize your expected reward, right? But if the means are unknown, then what should you do?
Pull each one for like some number of rounds.
Yeah.
See what like which arm gives them.
Yeah, so that's a very natural strategy. Actually, in fact, it's called explore then commit. So the idea behind that strategy is you pull an arm, each arm some n number of times, right? And you see, okay, which arm is doing better, which arm is doing worse, and then you commit to whichever is the best arm. Turns out it might not be like it might not be the optimal strategy. Because maybe you want to put less effort into arms which are not doing well, and maybe try to explore arms which are doing well, right? So this is called like traditional explore exploit trade-off where you basically want to like iteratively keep on exploring, but you can never be sure whether one arm is basically the best arm. So you want to focus your energy more on the arms which are doing well and try to sort of eliminate or not pull arms which are not good. Okay, so let me describe the problem formally. Okay, so you have n arms. This and you have each arm I. Okay. So Ri is drawn from Bernoulli of mu I. Okay. So this is basically called this is the mean of arm I, and you have a time horizon t. And for t is equal to 1 to t, you play arm it, and then you observe the reward. Oh, slightly bigger. So you okay. So this is the game basically. T is the number of, let's say, dollars that you have, and each dollar charge, like each machine charges $1, and each time you play an arm IT and you observe the reward, right? And what is your goal? So your goal is basically to maximize reward, but put it in a different way. You want to minimize regret, where the regret is defined as the summation of t is equal to 1 to t. So this is the mu star, which is basically max for all I, mu I. So this is the best you could have done in expectation, and basically okay. So this is the reward that you got, and this is basically uh, mu of it. So far, so good. So this is our notion of regret. In the literature, this is often called pseudo regret because we are taking the expectation over the reward. The actual regret is without this expectation. Like that's called bad. But we'll keep it simple. We'll define the pseudo regret. And one another note is that you you can generalize it to other distributions as well. I'll just keep it Bernoulli distribution for simplicity, but you can have any sub-Gaussian distribution and so on. Okay. So now let's look at basically the first policy that was proposed, right? So the explore then commit policy, okay, for this problem. And can you just reiterate what is the explore then commit policy?
Each arm for like
For n times, and then observe the reward.
maximally reward them.
Right. So let's look at the explore then commit policy. Okay, so For this policy, the and so
The speaker should write in bigger font.
okay. So even bigger. Okay. Sorry, my font size is not constant.
Multi-bandit is kind of right font size. Title font.
Okay. Okay. So for first m dot k times play each
It's capital N or small?
no capital N is the parameter for x. We'll choose this parameter.
K is the number of answers.
Oh, sorry. So this is a constant struggle with multi-arm bandits. Sometimes we use. I think I should use the K notation. Okay. Let's use the more standard notation. So play each arm in round robin manner. Okay. And then estimate the means mu hat I, basically, which is um, okay. So the mean is basically the number of successes you saw out of the n trials, and then you play the arm I hat, which is the arg max. That's a very simple strategy. Now let's see why does this work, right? So very quickly, for the theory audience, it's not too much of a it's like very familiar stuff. So the first step is basically to use our very familiar concentration inequalities. Okay. So
Size is the number of times R my quadrilateral of one.
one, yeah, Bernoulli, we are assuming Bernoulli. So it's basically so you can also replace it with the sum over the so average reward basically. Okay. So now let's dive into its analysis and basically why it works, right? And intuitively, the idea is that you would have estimated the means very well, right? And the means are estimated. The true means are close to the estimated means are close to the true means, right? And even though the true arm might have a better mean, you won't incur too much error. If n is big enough, you won't incur too much dependent on. Okay. So let's first start with our familiar concentration inequalities. So the first thing is that we'll show is that mu I minus I hat is greater than epsilon I is less than equal to this is a very familiar Hording's inequality. Does that make sense? So now we can set epsilon is equal to let me write it here. So we set epsilon is equal to 2 ln NT over n, and we take a union bound. What we get is that for all I, the probability that mu I minus mu hat I is greater than equal to epsilon is greater than equal to square root 2 ln T over n, and equal to 2k over some poly T or something, maybe T over 4. Does that make sense? Just a simple union bound, not too much of a big deal. Okay, so now this is basically the first step in the analysis. So the second step is very simple. You assume the good event. So we assume that the good event happened, meaning that this doesn't happen, right? And so now we want to understand how bad do we do, right? And the idea is very, very simple. So let's say
Writing it as a negative event.
Ah.
The quantity like probability there exists and I is this good is less than.
oh sorry.
That goes.
Sorry,
inside the-
yeah.
The fact that goes inside because
Yeah,
you're
sorry.
taking the.
Yeah, okay. Let me do it even. Yeah. Sorry for being sloppy, but this is what we do. Yeah. Okay. So it's very simple. So you have this mu star. Okay. And let's say you selected this guy, selected mu I. Okay. But somehow it happened that like the mu hat I jumped, right? And somehow like this guy dropped below, right? And you ended up selecting I instead of the I star. Okay. So you might suffer some regret in that case, but how bad can it be, right? So let's see. So let's define I star to be the arg max. And so there are few things that we know. We know that mu hat of I was greater than equal to mu hat of I star. So I is the arm. I know I set it to be mu hat somewhere. Sorry, I hat somewhere, but I'll just use I for simplicity. So I is the arm that you selected for the commit step, and we know that this quantity holds, right? Because yeah.
Sorry, I had a doubt on the previous thing. So the Hobding's inequality that you wrote was for a given I. So if you put that in, you will get for a given I, probability mu I minus mu I hat greater equal less than or equal to 2k by t power 4. So it should be multiplied by, let's say, all possible I or something.
The K on the right hand side.
Okay, k is for km, so you will put in.
Okay, so this is the first thing that we know. And the second thing that we know is that mu I is actually less than equal to mu of I star, right? Or pure mu star. Now, and the third thing that we know is that this thing holds, the good event holds. Then basically all these quantities are all the differences are less than 2 ln t. Okay. So let's call this quantity epsilon again. So we know that mu I plus epsilon is greater than equal to mu hat I, right? That's simply from this. Okay. And we know that mu hat I was greater than equal to mu hat of I star. And we ended up selecting I instead of I star. Okay. And the last thing is again use this guy. So we know that mu hat I star, mu I star minus epsilon. Just using this quantity. So this implies that mu I is greater than equal to mu I star minus epsilon, which is for us 2 ln t over. Oh, sorry, close. Yes. Okay. So now we are ready. Okay. So assume that the good event holds still. What is the regret? Can anyone tell me what will be the regret?
First, and round iterate to the atmosphere, and then
Yeah.
remaining you can.
Yeah, n times k rounds. It can the regret can each time can be at most 1, right? Because it's mu minus mu star. Okay, so this is less than equal to n times k, right? Plus right. So plus t minus n k. This is the remaining rounds, right? And then what we showed is that it can get most 2 epsilon. Okay. So then we can basically argue that yeah, this is simply like less than equal to n times k plus t into 2 epsilon. So let me write the full epsilon. Okay, so clear. Okay. So this quantity is, let's analyze what this quantity is, right? So I have something like this, right? So I have something like epsilon, roughly epsilon square k plus t times, sorry, k over epsilon square t times epsilon. Okay. If I set epsilon to be this is roughly 1 over epsilon square, right? And do you know how should I set epsilon? In other words, how should I set n for this to be minimized? Approximately equalize the two, right? So you want to set these two quantities to be equal, right? So you have k over epsilon squared is equal to t times epsilon. So this gives that epsilon is roughly k over t to the 1/3. Okay. So all in all, you set basically. So this epsilon gives a value of n, and you said basically n is equal to t over k 2/3. So this is sort of approximately, like, just to give you indication, there's a 2 ln t term also that you take care of. But this is the final sort of.
If like k is much smaller than t,
Yeah.
won't like n something like square root t be a better choice?
If k is much smaller than t, no, I think if k is even very small, if k is 2, even then this is a optimal choice. Even k is 2, this is like you want roughly.
Square root n in the
Yeah. But t is really the dominating thing. Yeah. Sorry. What did I do? Yeah. Yeah, because this t is the dominating thing.
If it was t by n instead of t
Huh.
by square root n.
T by n would be different. So, yeah. But you only have t minus n, which is enough. Okay. So if we plug this value of n, the final regret bound we get is basically, let me just do it here. I hope online people can be seen. This can be seen. This part of the board.
Yes.
Okay. Okay. So then we get RT is order t to the 2/3 and k ln t to the 1/3. Just plugging in the value of n, this is what we get. And so this is a high probability bound. So we with very high probability 1 minus 2k over t to the 4, we get this t to the 2/3 bound. And one can also show that this holds an expectation, right? If you take the expected regret, with 1 minus 2k over t to the 4, you get this regret. Plus with this small probability 2k over t to the 4, you can get some very high regret, but how high can it be? You can get most t. So this will be like a very small quantity as compared to this. So this is good. Okay. So now the question is, like, can you do better than this? Right. This turns out is not the minimum, the optimal regret that you can get. So, and it's kind of expected, right? Because you are sampling this sort of n times k is sort of the bottleneck, because you are actually exploring uniformly, and you're also exploring arms that are like completely rubbish, right? These are arms which you could have, even with like 10 trials, you could have realized that these are like very bad arms. You didn't need to be actually play them n times. Right. So can we have a more adaptive sort of a strategy where you initially explore, then you do some sort of realization that these are doing better, shift some weight on those, and then again do some adaptive thing, right? So so basically that's our next step, is to look at a better policy, which is called UCB, which is known to be like a very optimal policy, and it comes from the principle of optimism in the face of uncertainty. So let me start describing that policy, and if you have any questions about this, please feel free to ask before I jump to the next topic.
Typically, after this algorithm, like the factorial elimination or other scheme, or like what was the
Oh yeah.
chronology?
Yeah, I think after this algorithm, there was a successive elimination algorithm. And after that, it was like UCB1 algorithm, Euler et al. 2002, and then maybe several other variants of UCB. And after that, uh, people did a lot of like KL, divergence phase, and so on. Now it's a whole area of algorithms. Okay. One thing that I also want, Thompson sampling is like, yeah. Yeah, so I think in the series of development, like people always knew Thompson sampling is one like Bayesian type algorithm. And like 1930s, basically, Thompson came up with this algorithm, and it's a very simple and intuitive algorithm. You basically have a prior for all the arms. Let's say it's a beta prior, and each time you are sort of playing, you observe some reward, you update the posterior, right? And then essentially you sample each time when you have to play an arm, you sample from the posterior mean and play the highest mean arm, and over time it works. But the thing was that people didn't know the analysis of that algorithm for a long time, and people didn't sort of. These algorithms are much easier to analyze, like UCD style algorithm. So that was the case. Like these algorithms saw much more attention up until 2010-11, when people actually started trying to prove like regret bounds for the Thompson sampling algorithm, and I think 2011-12 was the first bound for Thompson sampling. That's when the development started on Thompson sampling as well. Empirically, actually, Thompson sampling works much better as compared to UCB. So,
IISc alumnus. Shipra was one of them.
Fipra was one of the,
And nothing.
yeah, it's one of the. People also, there was other people as well who sort of simultaneously, uh, I think, had the result. But I think they are one of the first published papers.
What's the state of the art was Thompson? I mean, is this analysis complete or?
Yeah, it's pretty complete.
Yeah.
I think it's a very frequentist analysis though. But yeah, people have understood quite a bit. The subsequent work by David Columbia. So yeah, lots of work on something happening. But yeah, now people understand it very clearly. Yeah. I didn't want to go into Thompson sampling today because it sort of takes us away from the next section, because these are the two algorithms that are important to understand the sort of. So let me sort of put a disclaimer. This is termed as intro to multi-arm bandits. This is not like a proper intro to multi-arm bandits. This is sort of building a background on what is to come next. Yeah. Okay. Okay. So now we'll look at the UCB algorithm. There are several variants of UCB as well.
The previous algorithm is not known.
Yeah, the previous algorithm, if T is not known, you can do some sort of a doubling or geometric trick. that this is very easy actually. UCB, if T is not known, you don't have to do any doubling or anything. So I'll tell you how it sort of works. But for us, let us assume that T is known. I'll tell you where exactly the change happens. Okay. Yeah, so this algorithm was a very nice and intuitive algorithm. It's based on this principle of optimism in the face of uncertainty. So you have the means are uncertain, right? And you want to understand like what is the sort of maximum performance or what is the best one particular arm can be, right? So let's say you are in the middle somewhere of your time horizon, and let's say these are the sort of so this is mu I. So what you do is you calculate the confidence intervals for each arm. Okay. So let's say you're at some time t. What you do is you calculate this confidence interval, and you always choose the arm that has the highest upper confidence. Okay. So in this case, this has the highest upper confidence. You will choose this arm over this arm. Okay. Even though the actually this is empirical mean. Even though the empirical mean for this guy is larger than this guy, okay, you will still choose this arm because essentially what the reason why this confidence, this sort of confidence interval is so large is because this arm has not been explored enough, right? So maybe since it is not explored enough, maybe the actual mean is much higher, right? So this sort of balances this explore-exploit trade-off. Because suppose if all the confidence intervals are very small, meaning that everything has been equally explored, then you kind of go with the best arm that has the best mean. But if this is the situation where some arms are not very well explored, right, and they have very huge confidence interval, you'll go for those arms because maybe the potential is high there. Here you already know something about this. Okay. So this is sort of the principle of optimism in the face of uncertainty. And in terms of sort of um, actual algorithm, it's very simple to describe.
The confidence beforehand for all the arms and then
It's the confidence.
the
No, confidence bound is based on the sort of the concentration inequality. Like it's based on so you calculate the confidence interval, right, based on the number of samples that you have so far. Right? If you have huge number of samples, then the confidence interval is very big.
in that case, how do we compare the
If you define confidence interval.
Yeah, that's what I was going to do that. Yeah. Okay, so this is basically and this guy is okay. So you define this upper confidence like this, right? So upper confidence is the empirical mean, which we just saw, right? This is the number of successes that you have had before time t, and NIT is the basically the number of times you've pulled arm I till time t. So this is a random variable, and this is the confidence interval that you're talking about, and it's defined based on the number of times that arm I has been pulled. So this is the upper confidence one. Similarly, you can define the lower confidence one.
I mean, like what basically kind of like does it come from the inequality, housing inequality, or
Yes. Yeah. It comes from that. Yeah. So yeah, so I'm just describing the algorithm first, and then we'll go into the analysis. And your intuition is correct. This you can basically get from the Hawking's inequality. So there are many ways to calculate confidence intervals, but stick to the Hawking's. Okay, so now let's look at the analysis of this algorithm. Okay, so the first step is the same, apply Hawking's inequality. Okay, so we have that the probability that mu I minus mu hat I. Note that there is a t here because mu hat I keeps changing as time changes, is greater than some epsilon. Okay. Now note that we cannot like directly apply Hawking's inequality here. Can anyone tell me the reason for that? Ni is a random variable, right? So you cannot have e to the minus n because okay. So there are many ways to deal with this. We'll use the very simple way. So we'll use a union bound. So we'll have something like this. So this is less than equal to summation. So actually, let me. This is the change that I'm doing. So basically, the NIT can take like 3 different values. So if you play this arm, this one arm all the way, then it can be T. It can be somewhere in the middle. So this is the all possible values of NIT. And then you have just the same quantity, but I'm replacing the mu hat IT with mu hat IK. Okay. So think of mu hat IK as the mean of the same random variable after k samples. Okay. And that NITK, which is basically the number of times it has been pulled, is equal to k. This is small t. K is equal to 1 to, yeah, you can also have it till small t. That's also fine. But yeah. Okay. So this is kind of simple, and then you can just remove this because it can only increase the probability.
Some other big K is overloaded, maybe J or something. S.
K is
Number one.
Small K, capital K.
K, yeah.
Okay.
Yeah, this is usually capital K,
Okay.
but let me just use M. Okay. Sum of, yeah, sum of K. Okay, now we have already seen this. This is
Equality.
this guy.
Yeah.
Yeah, actually, this is the equality. Uh, yeah, actually, you are right. Yeah, this is a mutually disjoint image. Yeah, so, yeah. Okay, so that's great. And then we have seen this before already. This is less than equal to e to the minus this is m, so m epsilon square. Okay, and we also have t here. So this is t because of the union bound. And if we set m, so we set epsilon is equal to, let's start here. So epsilon is equal to the same kind of value.
How is it? Which M are you choosing for that? Right?
Oh, sorry. Again, I'm too soon. Okay. Epsilon is equal to square root 2 ln t over m. And plug this in. What we get is this guy is less than equal to.
M is a rest variable supplement.
Sorry, what?
Epsilon is a single number, whereas M is different values. So, yeah, but
So m is a, yeah.
this command, it's
You can call it epsilon m. No, wait. No. You are right. Actually, I try to sort of let me not put in epsilon. Try to sort of make it succinct, but I think this is what I'm on. This is what we wanted, right? And so I just want to have this. Okay. And then from this we get that this is less than equal to 1 over t to the 3 or 2 over 2 to the 3. Now this is correct. And they use this also at 2. Okay. So, and then we can again take a union bound. And in the interest of time, I will not. So again, we have that probability that exists I such that mu I minus mu at IT is greater than 2 ln t over NIT is less than equal to 1, 2k over t to the 3. Okay. We have this. Now let's analyze the regret. So the regret is the following. So RT is equal to summation over I is equal to 1 to k. Yeah.
So the algorithm, it's so for t equals 1 to t, compute UTB of I. So what will the initial upper controls going to be?
Yeah. So that's a very good question. Actually, I just glossed over that. So you just play each arm once.
Okay.
Yeah. Assume Ni0 is like 1.
Okay.
Yeah. Okay. So that's cool. And I also wanted to get to one point. So you said if you don't know the time horizon, you can just replace this capital T by small t. And that'll work perfectly. Yeah. So that's basically very easy. Let's get back to the regret. So summation over t is equal to 1 to t. We have that.
What do you mean by we don't know capital T? I mean, what is that setting?
Oh, so yeah. So the idea is that let's say you are running this experiment, and so let me give you a practical setting maybe. So this is, for example, used for what is called A/B testing and so on. So you have 10 different variants of your product, or let's say you're designing a website and you have 10 different layouts and you want to see which layout is the best for me. And then you can do the following. You can just try this algorithm. So each layout has some reward, right? So each layout is, let's say, like what is the average probability with which people like that layout, and you want to find the best one. So you can do run this using algorithm. You don't know the time horizon up until maybe you want to run it. Maybe you want to run it like for 2 months or 3 months and so on. So there are settings where you don't know the time horizon upfront, and you want to experiment up until like you are confident, or maybe you see these like the confidence level become very small. You're very confident about the best now. So those would be settings where you don't know the time horizon upfront. But then there are also settings where you know the time horizon upfront. So if you don't know, then you just put t here, small t here. Okay, so this is okay. So I sort of reformulated the regret as this. Okay, so this is sum over all arms k 1 to k. T is equal to 1 to t. What is whether arm I was played at round t or not, and what was the sort of regret. And this delta I t term is basically the mu star minus mu it. Okay. Now in this, the only sort of step is to bound this, and we'll do a similar thing as before in order to bound this, right? Again, this type of a picture will sort of become important. So you have some mu star, right? Which is the optimal arm, but you played some mu I. So you played mu I at time t, okay? And somehow the upper confidence bound for mu I was this, and for this maybe it was something lower. Okay. And you ended up playing this. Right? Oh, sorry. It's good. Okay. Yeah, it's always guaranteed to be higher than this because of this high probability event. With low probability, it can be. Okay. So now the only thing is you have to bound the difference between mu star and mu I. Okay, given the fact that you played I at round t. Okay. If you are not given this fact, then the difference can be Q. But you have to use somehow the fact that you played I at round t, and the UCB had to be higher for IT. So now basically assume the good. Assume good event, and in that case, you know that each arm is bounded like this. So each empirical mean is bounded like this. So there are two things that you know.
I was taking union boundary. You have this good event for every small t.
For every small t, yes. Yes.
Becomes t square or something.
Oh yeah, that's an important step that I sort of forgot. Okay. Yes. I need to take another union bound. And then this will be another. Yeah, important step. We need a union bound over all t as well. Because even if this thing fails for one round, then it would be problematic for us. So you want this union bound for all t, and then you assume a good event, and in that case, what you know is the following: mu I is greater than equal to. So I was played at round t. Remember that. So I'm defining epsilon IT is equal to and I'll try to make this a consistent definition. Okay, So this is by the good event, like directly by the good event, that the mean has to be larger than this, right? And so then we have uh, this important fact that UCB of I at time t is greater than equal to the UCB of I star at time t. Okay. Because this is by the selection rule. You're always selecting according to this rule. Okay. So this implies that mu I, this is greater than equal to mu, let me actually, yeah. So this is basically mu hat I at time t. Okay, so this is clear, right? This is just the definition of UCBI, and we will use this here. Okay, so this will give us mu hat I t is greater than equal to mu hat I star t plus epsilon I star t minus epsilon I t. And then we'll try to plug this in here. So this would be mu. So this is this quantity. So we'll have mu hat I star t plus epsilon I star t minus 2 epsilon I t. Okay, just look at it and see if it makes sense. So it's very simple algebra. Okay, any questions? You just use the UCD rule, you arrived at this bound, and then you already had this by the good event. Mu I is greater than mu hat IT minus epsilon I. And then you use this bound here, you get this. Now, this guy is basically, I'll just argue that this guy is what? Is greater than equal to. Can you tell me what this guy is greater than equal to? This comment. Mu star, right? Why?
Good event also.
Yeah. So mu I star minus 2 epsilon I t. Okay, so far so good. So we found our value of delta, right? So then let's just so what we just showed is that delta IT is equal to 2 epsilon IT, which is equal to this quantity. So what we get is that the regret is less than equal to summation I is equal to 1 to k, summation t is equal to 1 to t. Okay, so is there a way I can rewrite this? So I'll claim that this is the particular way that I can rewrite this. So this is going to be summation I is equal to 1 to k, summation m is equal to 1 to nit. So note that this is capital T. Okay, and square root 2 ln t over n.
We do this just to kind of get short and time.
Yeah.
So I thought delta IT was just being as a deterministic quantity.
Oh yeah, so this is slightly overload of notation. Yes, so that's right. So how? Okay. So delta IT is a deterministic quantity.
Delta T might come.
So delta IT, this is a deterministic quantity, but our bound on this quantity is not deterministic. Does that make sense? Because we are using the fact that we played I at round T, right? And since we played at I at round T, the bound changes according to whether it was which round it was played at. So even though this is like a fixed constant, but our bound on it is variable. Depends on the particular thing. Because we're using the fact that since it was played at round T, the UCB like of IT should have been higher and so on, and then we get this bound based on that. Okay, so this, does everyone see that this is how to get from here to here? This is just a simple rewriting.
What is M?
M is this summand. Okay, because see, each I will appear, so at every single time only one I will appear, and you have like roughly 1 over NIT. Okay, so you'll have sums like these 1 over 1, square root 1 over 1, square root 1 over 2, square root 1 over 3, right? For each I up until the final like number NIT. Okay, so this is just a simple rewriting of this. Okay, so this is kind of a very nice proof, one of the very nicest proof of UCB. And I really like the first time I saw this. I really like this. It's very very clean. Okay. So now this quantity I will claim is basically simply upper bounded by square root NIT. Okay. Because you have something like this, right? Square root 1 over 1 plus square root 1 over 2 up until like 1 over square root NIT. There are square root NIT terms, right? And the maximum term is basically, sorry, there are this is supposed to be easy, sorry, what? There are NIT terms.
We take square root NIT terms together and round it to 1.
What is this?
You can just upper bounded by like 1 over square root x integral 1 over square root x going from 1 to capital T, and you get
1 over,
you just upper bound this as integral.
okay.
This x goes from 1 to NIT 1 over square root x. We instead of finite sum, you are upper bounding it by integral. So this is going to be square root of NIT minus 1.
Yeah. Yes. Okay. So thanks for saving the day. This is, yeah, this is not a simple, like not as simple. You do need an integration here. Okay. But after this is simple enough. So then this should be bounded by square root k t times 2 ln t.
It's actually an upper boundary.
Okay.
Boundary upper boundary.
Okay, so why is that? Can anyone, like, how do you get from here to here? NIT, sum over all NIT is upper bounded by T. Or she should say. Okay. So that's our high probability bound. We're doing much better than T to the 2/3. Okay, so we are already a bit late, but maybe we can continue in the next lecture. But basically, this was a brief introduction, and this sort of nice bound on nice proof of the UCV algorithm. That's sort of what I wanted to get across. There's like it's a huge subject, and if you want to go into depth, there's so much.
This is what's a good reference for this particular group because this Bandit Wilson's book has a different one, right? Latin's book has it. This is from Latin.
I actually don't know. I think Slipke's book also has a different proof. I think. Okay, so one thing that I actually importantly wanted to point out is that this is not the only proof for UCL Gotham. There are many more proofs. There is also instantaneous bounds. Okay, this is called instance wise bounds. This is called an instance dependent bound because you are not the final bound doesn't depend on the mu wise. There are instance wise bounds as well where the final regret depends on the specific mu I or delta i's. But this is like a nicely instance independent bound. You get this deterministic quantity. Sometimes the instance wise bounds can be tighter, but it depends on the gap between different quantities. This is in terms of just K and P. For a nice reference for this.